In this video, we're talking about metal. Okay, now that we got that joke out of the way, in this video, we'll be talking about what metals are and what they're really good at doing, which is conducting electricity. The story of electricity is about how our modern world was set up and the race to generate affordable but safe electricity for people to consume. When the 1800s began, people would light their homes with gas, and electricity was too uncontrolled to be brought into their homes safely. But by the 1900s, the world was rapidly electrifying due to breakthroughs in chemistry and engineering, and this would lead to a rivalry between two currents, AC and DC. Okay, I promise I'll stop. The person who would bring electric power to people's homes in the 1880s and 90s would be the most rich and famous in the land. This was the dawn of the age of electric power and light, and would see one of the most brutal engineering rivalries in history, known as the War of the Current. So, to understand what electricity is and how it flows, I'll start with a strange discovery and the easiest Nobel Prize that was ever earned. If you would ask any scientist 20 years ago, what is the most electrically conducting element, they would have said silver. And the only reason we don't use it in our electronics today is that copper is cheaper. But then in 2004, two physicists made another element conduct better than silver with just a piece of Scotch tape. Two Russian physicists were working with graphite, the soft form of carbon used to make pencil cores. Because graphite is a brittle material, it becomes flaky, and scientists were using Scotch tape to clean up their samples. By sticking tape to graphite and then peeling the graphite off, the result was a shiny new surface, which gave the scientists a new idea. If you stick a piece of Scotch tape to an already clean surface of graphite, you can extract a layer of carbon which is just one atom thick. This substance, which they named graphene, is arranged like a chicken wire chain link fence of carbon atoms, and this gives it unusual properties. Not only is it 200 times stronger than steel, it is transparent and has an electrical conductivity better than silver. We measure conductivity in units called Siemens per meter. Silver has a conductivity of 60 million Siemens per meter, and graphene clocks in even faster. What's surprising about all this is that carbon is not a metal, and it's usually only metals that can conduct electricity. So what's going on here? What picture comes into your mind when I say the word metal? Probably a gray solid that is hard and shiny. But that picture is probably of steel, titanium, aluminum, or chromium, the four most common metals in our everyday life. But metal as a category is very broad and has all sorts of appearances and properties. Bismuth forms square crystals which glisten like oil, while lutetium and thulium are found in clumps that look like corned beef. Niobium is a dull silver color when it's isolated, but becomes a rainbow color when an electrical charge is passed through it. Some metals like iron show magnetism, while some like neodymium are not magnetic but will reinforce the property in other metals. Tungsten can remain solid when heated to over 3000 degrees Celsius, or gallium, which will melt in the palm of your hand.
With such a broad spectrum of behavior, what is it that unites all metals?
The answer is that a metal will conduct electricity. Carbon will conduct electricity when it's in the graphene state, but a metal will conduct no matter what state they're in. And so to understand metal, we need to understand electricity, and for that, we need to talk about Pharaoh.
When the Kingdom of Egypt was united for the first time, in 3100 BCE, the first pharaoh who ruled was named Narmer. Now there's a lot of debate about his identity, but his name translates into English as Angry Catfish.
Now, it may seem weird that the ruler of a land would adopt such a weird name, but in ancient Egypt, the catfish was the protector of the Nile. And although the word catfish has a very different meaning today, and the fish itself doesn't really seem that remarkable, the catfish found in Egypt is special. Its scientific name is Moloptereris electricus, which means the electric catfish.
Like the eel of South America, this creature is able to deliver a 400-volt shock in one touch against the skin. And so records of electricity can be traced back to 5,000 years ago. But it would be a while before humans would be able to control this phenomenon.
The word electricity traces back to ancient Greece, to an early scientist named Thales. He discovered that by rubbing a gemstone called amber onto wool, that it developed a crackly property which would spark every so often. But a true understanding of this force as we know it today, which is that it flows as a current, would start with the English experimenter Stephen Gray. In the 17th century, Gray was working with a glass rod and rabbit fur to generate static electricity.
His experiments consisted of rubbing a glass rod on rabbit fur and tapping it on whatever was around him in hopes of creating a shock. Gray noticed that when he put the end of a rod into a piece of cork and then used the cork to tap feathers, they would spark. The glass was able to transfer the electricity through the cork. And so whatever electricity was, it could flow like water, so we call it a current.
After repeating the experiment with several different items, Gray began to divide everything in the world into two categories: insulators, which would not let the flow of electricity, and conductors, which would. And it turns out that the best conductors are metals, which today are found along the left side of the periodic table. So why are metals such good conductors of electricity, and what is electricity itself? The answer to this question is important because it has changed billions of lives forever and affects everything that we do today, including watching this video. So as the world raced to electrify at the end of the 1800s, a war of the current would break out, which would be one of the most brutal marketing campaigns in history. But to understand this war, we need to first take a quick crash course in quantum mechanics. The first thing to say about quantum mechanics is that it's not one idea, but rather a collection of theories which explain the world at its most basic level. The behavior of electrons, the nucleus of an atom, light, and the interactions between all these things is explained by quantum mechanical theory and is therefore foundational to chemistry. I'm just going to focus on one detail that helped build the periodic table, and that is the Schrödinger equation, which was made by Austrian physicist Erwin Schrödinger.
An atom has a heavy center called the nucleus, which has a positive charge, while electrons surround it because they have a negative charge and are attracted towards the nucleus. The Schrödinger equation tells us where the electrons are likely to be as they fly around the nucleus, and the 3D image shows us that electrons surround the nucleus in different shapes, and the spaces that they take up look like electron clouds and are called orbitals. Depending on how many electrons there are in an atom will affect how many orbitals an atom has, and by extension, the shape of that atom. The different shapes of atoms explains why there are different behaviors of the elements, like being an insulator or conducting electrical current.
In quantum mechanics, the word energy describes the ability of a beam of light to push an electron to an outer orbital. And the opposite of ability is stability, which means that an electron is settled and doesn't want to move. And so an electron that is closer to the nucleus will be settled in its orbital and will not change, and is therefore described as chemically stable, while an electron in an outer orbital has more of an ability to change if it's given the chance, and is therefore described as unstable. The basis of chemistry could be demonstrated by this coat on a hook. And although this coat will hang here, it would be more stable if it was laying on the floor. But in order for that to happen, we need to put some energy into the system and push it off the hook. Now, although I'm happier when my coat is hanging on the hook, thank you very much, in quantum mechanical terms, the coat is happier after it falls.
Electrons are the same way. When we excite them, electrons can leave their orbitals and find new stable ones. Some substances like water have a very long hook and will always fall back onto the hook, and so it's not very reactive. The active ingredient in dynamite, in contrast, has a very short hook, and so a little nudge is enough to make it release a lot of energy. And so the art of chemistry is knowing how the electrons will rearrange when they fall into stable positions.
For an electron to change its orbital is not a rare event. In fact, it happens any time that two surfaces meet. But when these surfaces are separated, the electrons return to how they were. But some molecules like to hold on to electrons more than others, and so they don't let the electrons return. And a great example of this is rubbing a balloon into your hair.
Hair is very bad at holding electrons, while rubber is very good at it. So by rubbing it on your hair, this excites the electrons, allowing them to rearrange. Since rubber is a good holder of electrons, it becomes negatively charged, while the hair becomes positively charged, with a charge imbalance occurring and a bond being created.
Now, normally, your hair and the balloon don't have an electric charge, and this is because the atoms are balanced out between their protons and electrons. But when the electrons transfer from your hair to the rubber, the balloon now has an electron surplus while your hair has an electron deficit. Now, it may seem weird to say that this is somehow a more stable arrangement of electrons, since the balloon stole the electrons from your hair. But this is the same concept as saying that a coat is happier after it falls. And so when Stephen Gray rubbed glass on rabbit fur, he was depositing electrons onto the glass since it's an insulator and can hold the electrons, and the cork was acting like a conductor, allowing the electrons to flow. And so wires, which allow electrons to travel through them, are an extension of this very same concept.
Let's look at the periodic table. As you go across from left to right, the amount of protons in each element increases, meaning that the size of the nucleus increases. As the positive charge increases, this attracts the negative electrons inwards, causing the atom to become smaller. By looking at a periodic table of atomic radius, we see this decrease in atomic size across each row from left to right. Atoms on the left are big, with open orbitals, and since the electrons are a long way from the nucleus, they become ideal for sharing with other atoms. The atoms on the left of the periodic table are the metals, and they are eager to share their electrons in what is essentially one mega-orbital, which physicists refer to as the sea of electrons. This network of overlapping orbitals means electrons can easily move from one side of the metal to the other. In the smaller molecules on the right side of the table, the orbitals are much smaller and closer together, so they won't really conduct electricity under normal circumstances. So any substance that can conduct over 1 million Siemens per meter is classified as a conductor, while the substances that are below 0.01 Siemens per meter is an insulator, and anything that falls in between is called a semiconductor.
And so whether a substance is a solid, liquid, or gas depends on how much its atoms are attracted towards each other. And this attraction is called electronegativity. So the element oxygen, which does not have a lot of interaction between its atoms, is stable as a gas at standard temperature and pressure. But metals, by contrast, will interact with each other, and so they'll be stable as solids at STP. The obvious exception to this is mercury, which is a liquid at STP, and this again is due to the arrangement of its orbitals, which are shaped like petals on a flower. And so this allows the atoms to interact enough in order to conduct an electrical current, but not enough for it to be held together as a solid. And so now that we know what a metal is and how it conducts electricity, we can get to the current war. As the world began to electrify in the 1880s and 90s, there were really two ways to distribute electricity. This would be the famous conflict between Thomas Edison versus Nikola Tesla and George Westinghouse. To understand the rivalry between Edison's electricity and Tesla's, we begin with a discovery in the 1700s made by an all-time science great, Michael Faraday.
Experiments had shown that an electric charge could affect a magnet, and that these two seemingly separate forces were in fact related in what was called electromagnetism. Faraday conducted an experiment where he spun a conducting metal plate through a magnetic field which generated electricity. Since electricity and magnetism were connected, By using one, you can generate the other. The movement of the plate caused the electrons to get excited in quantum mechanical terms and to change their orbitals by moving to the outer edge of the plate. When this generator was connected to a wire, the electrons would flow freely through the metal as a continuous current.
The flowing of electricity through a wire would revolutionize the world several times. For example, the invention of the telegram, which allowed for seemingly instant communication worldwide. But this also allowed for electricity to be distributed in small and safe amounts and to be brought into people's homes. And this would allow for another invention, the incandescent light bulb.
The design was to pass an electric current through a filament, which is a material that the electrical current has more difficulty flowing through than the copper wire in the rest of the circuit. As electrons travel through the filament, they don't move in perfect lines, so conductivity doesn't always happen smoothly. When the current requires more energy to pass, we use the word resistance to measure the increase in heat which causes the filament to glow, which is called its voltage. The challenge was to find the best filament.
Coconut fibers and horn shavings of fishing lines, cork and celluloid of flax and platinum, iron, nickel, copper, steel. We scoured the earth years and years trying thousands, 10,000 different combinations. And George Westinghouse saw how he did it and put on a pirate hat. Oh, you got vultures in every venture, but you just got to keep them away.
If you ask most people who invented the light bulb, they would probably say Edison. But in fact, many designs for the light bulb already existed. Edison and his team in Menlo Park in the US and Joseph Swan in the UK perfected the design for the light bulb by testing many materials for the filaments and creating a vacuum seal bulb which allowed the filament to get hot without burning out.
What set Edison apart is that he distributed the electricity for his light bulb from a central power station and created an entire system of selling cables, sockets, and meters for his direct current, or DC, to be distributed across New York City.
The reason why the story doesn't end here is because there is a major flaw with Edison's electric current. A direct current could only reach about a mile away from the power station, and this made it safer if someone was going to touch it, but it made it less efficient and more expensive.
Enter Nikola Tesla. His system would solve Edison's problem with what he called an alternating current, or AC, which moves back and forth quickly rather than in one direction all the time. This would raise the voltage, meaning less resistance, which would allow the wires to be longer and distributed over larger areas. But before the wires come into the home at such a high voltage, they would be converted using a transformer, which would allow people to consume it.
This allowed for the transmission of electricity far from where it was generated, and this system was pioneered in the US by the businessman George Westinghouse. He made an offer to Tesla for the patents to his alternating current motor.
You know that when I first came to this country, I worked for Mr. Edison.
I did not.
T?
Sure.
I fixed 2 of his DC generators in one night, and he called me a damn good man. So why did he not treat me that way? I quit, tried my own company, and was deceived. But was I, some immigrant. So I took the only job I could find, digging a ditch. The men laughed at my fine clothes, but at the end of the day, I had $2.
What was the ditch to be used for?
Edison Electric. Felt like digging my own grave. If Mr. Edison succeeds, he will set us back so far we may never recover. The fare must be alternating. It must be my motor.
I'll give you $2.50 per horsepower. I'm no genius myself, but that should be millions.
But instead of AC being adopted nationwide, DC stayed on the market for many years, mostly due to Thomas Edison himself. You see, Thomas Edison and George Westinghouse were in a race to light up America, and this is what's known as the War of the Currents. Edison's DC cable were low voltage, and so they would be safe if someone touched them directly. But Westinghouse's AC cables were high voltage, and so they would be deadly if someone touched them directly. And so Edison continued to paint his DC cables as safe, while the other AC cables were deadly. And this played into the fear of many people about electricity.
Thank you, Mr. Edison. And thanks for this.
Did I mention that his system is lethal? When you reach out and touch a doorknob or a rail, and well, you become the circuit.
Just to be clear on that point.
Will you die? With DC current, you can reach out and touch anything at any stage of the line. And with your bare hands, it's safe, it works, and it bears the name of Edison, so it's pretty. Our government has been trying for some time now to get me to invent a weapon. But I won't use this brain to invent anything that hurts people. For that, you can shop in Pittsburgh.
So you say Westinghouse wants to hurt people?
No, I can't say that. But you can.
In 1886, the American Human Rights Committee decided that the execution of criminals by hanging was inhumane, and that a new method of capital punishment was needed. In the most morbid marketing strategy ever used, Edison insisted that the new electric chair should be configured to run on Westinghouse electricity, so people would associate that current with death. Edison and others also tested killing animals with AC, including a circus elephant, which he was kind enough to film. And soon, the electric chair was used on its first victim in 1890.
Gus is being connected to the same current that Westinghouse uses for his generator. But there's no word yet coined to define death by electricity, so I asked the men who write the dictionaries, and I heard back electrochromate, and dynamort. But just as Joe Guillotine got his name on his invention, how could we rob the rightful inventor of death by electricity of his due credit? I ask you to please be respectful as we Westinghouse this horse.
Right now, I'm standing near the site of the first power station that was built by Thomas Edison. He started the electrification of New York City, but ultimately the system that we use today would be pioneered under Nikola Tesla and George Westinghouse.
In 1896, the first hydroelectric power plant was completed at Niagara Falls, using Westinghouse generators to create Tesla's AC current. Finally, the war of the current had been won, and the energy from Niagara Falls was distributed to cities nearby like Buffalo and New York City. Edison's company would go on to form part of General Electric, while Nikola Tesla would die in relative poverty, but it would be his genius that would provide electricity to billions worldwide.